In section 3.7, we're going to look at implicit functions and taking derivatives implicitly. So in this section, we're going to differentiate implicit functions, and we're going to use the chain rule to find the derivatives of implicitly defined functions. So let's start with a little exercise, just finding some common derivatives, and then we're going to look at some kind of uncommon derivatives at the end. So first, let's think about how to find the derivative of x squared. In this case, this is just a simple derivative. This is going to be 2x. So let's make it a little more difficult. Let's think about quantity 2x squared. And we can do this algebraically, writing this as 4x squared, but let's use the chain rule. And in fact, we're going to use the chain rule for everything else here. So in the chain rule, the outside function in all these cases is something squared. The inside function changes. Here we have 2x. So the derivative is going to be the derivative of the outside, 2 times the something. We're going to leave the inside alone, and we're going to multiply by the derivative of the inside function. This is going to give us 2 times 2x, in this case, times 2. All right, so let's do it again. How about sine squared? Here, the inside function is sine. Outside function is something squared. So the derivative is going to be 2, in this case, sine, leaving the inside alone, and then times the derivative of sine. And this will give us 2 sine, 2 sine times the derivative of sine, which is cosine. All right, what if we had something really weird in there? Let's do a little tornado squared. Here, the inside function is this tornado. And we're going to have the derivative is going to be the derivative of the outside function, leave the inside function alone, and we're going to multiply by the derivative of the inside function. Now, I have no idea what derivative of tornado is, but the point is that we could do this kind of process for literally anything. So now let's do it for y squared. Here, the inside function is y, so the derivative should be 2, inside function is y, times the derivative of y. And we could write this one as 2y dy dx, moving the y into the numerator. And this is what we're going to be focusing on. This is implicit differentiation. And the idea is that y is a function of x, like y equals f of x. So when we're doing the derivative of y squared, it's like we're doing the derivative of f of x squared, which is 2 f of x times the derivative. But we're just writing it in terms of y, and there's reasons for that because sometimes we can't define a function. But this is implicit differentiation, doing derivatives like this. And the next example is going to show why we need to do something like this. So, find the equation of the tangent line of a circle of radius 5 centered at the origin. The equation of that circle is x squared plus y squared equals 25, where 25 is 5 squared. And we're going to find the tangent line at the point 3, 4. So first, let's see if we can even draw this, and then we're going to try to find the equation of it. So 3, 4, we have this point right here on the circle, and the tangent line is going to be the line that kind of hits that circle at one point and then goes off in a different direction, or it goes off in the different directions. So there is the tangent line that we need to find. This is the tangent line of x squared plus y squared equals 25 at the point 3, 4. But the problem is that this function, x squared plus y squared, this should be 25, is not a well-defined function of x. And the reason it's not, for one reason, is that it doesn't pass the vertical line test. It hits the function twice. Right? This is not a function of x. So therefore, we can't write this as f of x or f prime of x. But yet, we can still think about a tangent line here. It wasn't that hard to do. So how can we figure out what that equation is? Well, there's going to be two ways we're going to do it. One is the old way, and I want to just go through this just to kind of see how we could take care of this specific problem, but then know that this process does not work in general. And a lot of other questions we're going to look at in this section, this will not work. So the way we could do it is that we could solve for y and then find a normal derivative. So we could write this as y squared equals 25 minus x squared, and then y equals plus or minus the square root of 25 minus x squared. All right, and note that what we're trying to find is the derivative of this thing, right? Y equals plus or minus 25 square root of 25 minus x squared. And this plus or minus is a problem. Right? That is not a function having that plus or minus there. So the reason why this works, this particular problem, is because we can break up this circle into two different functions. We have the top of the circle is y equals square root of 25 minus x squared. And the bottom of the circle is y equals negative square root of 25 minus x squared. So for this problem, since 3, 4 is on the top half of the circle, then we can just use the function y equals square root of 25 minus x squared. So this is our function of x. So if we want to find the derivative, then we're going to take the derivative of this, and this is going to be chain rule. Outside function is square root of something. Inside is 25 minus x squared. The derivative of square root of something is going to be 1 over 2 square root of something. And this is going to give us 1 over 2 square root of 25 minus x squared times the derivative 25 minus x squared, which in total is going to give us a negative 2x, that's the derivative of 25 minus x squared, over 2 square root of 25 minus x squared. So this is how we could find the derivative, and we could find the tangent line from that point. But this is our old way of doing it, and it's a little bit awkward, and we got lucky because there's this plus or minus part of the equation we were able to work through. So now let's think about doing this a new way to find the derivative and then the equation of the tangent line. And this is going to be differentiating implicitly. So we're not going to mess with the equation x squared plus y squared equals 25. We are instead just going to take the derivative at that point. We're going to have to deal with a derivative of y in some case. So remember, what we're trying to find here is f prime. That's the derivative. And note that we could rewrite the derivative as ddx of f of x. We often rewrite f of x with y, so there's ddx of y. And then if we bring the y into the numerator, we get dy dx. So this is the derivative. And that's what we're going to be trying to find. We're going to try to find dy dx if x squared plus y squared equals 25. So the process, what we're going to do is we're going to start with our equation. And we are going to take the derivative with respect to x of both sides. And this derivative is going to be equal to the derivative of x squared plus the derivative of y squared equals the derivative of 25, which is just 0. So the derivative of x squared is going to be just 2x. And then we did the derivative of y squared before. Remember, we have to use the chain rule. This derivative is going to be 2y times the derivative of y, dy dx. And this is all going to be equal to 0. So let's recall from the first page. If we want to do the derivative of y squared, we have to use the chain rule. We have the inside function is y. We have the outside function is something squared. So we take the derivative of the outside. We leave the inside function alone, and we multiply by the derivative of the inside, except now we can just rewrite this ddx of y as dy dx. So now we're going to use this expression. Remember, what we're trying to find is dy dx. So we are going to solve for dy dx in this expression. So I'm going to subtract 2x on both sides, and we'll get 2y dy dx equals negative 2x. And then I'm going to divide by 2y, and this will give me dy dx is equal to negative 2x over 2y, or negative x over y. So there is our derivative written in terms of both x and y. And we did this implicitly. So now we can finish off the problem. We have the derivative. Now let's think about the original problem. Find the equation of the tangent line of a circle of radius 5, centered at the origin. That's x squared plus y squared equals 25 at the point 3, 4. So we know that the derivative here is going to be negative x over y. This gives us the slope of the tangent line at the point x comma y. So the slope of our tangent line is we're going to do dy dx evaluated at x equals 3 and y equals 4. That's going to be negative 3/4. slope of the line here. Remember, what we're trying to find is the equation of this line right here. And now we've found that the slope of this line is negative 3/4. Remember that the equation of the tangent line is y equals f of a plus f prime of a times x minus a. This a value, this is the x value that we're thinking about. This f of a is the y value. And then, of course, the f prime of a is the slope. So the x value in our case is x equals 3. The y value is y equals 4. And the slope we found was negative 3/4. So the equation of this line is y equals 4 minus 3/4 x minus 3. Note that with this, we could easily find the slope of the tangent line at a different point. It doesn't have to necessarily be on the top half of the circle. We can do it for the entire circle, which we weren't able to do in the first kind of iteration of this. Doing implicit differentiation can be challenging at the beginning because it's new, but the biggest sort of hurdle we need to get over is that y is a function of x. And we kind of mix around that notation a lot earlier in algebra or pre-calc, and now we need to do it a little more comfortably. In the next video, we're going to go over a bunch of practice problems to be better at implicit differentiation with some more complicated functions.